Today I've got a problem suggested from our channel's favorite problem suggester. And what we'll do is get a series representation of the secant function, 1 over cosine. Notice I didn't say a power series because it's not exactly a power series, but it is some sort of infinite series. And maybe one of the most interesting things about this is, well, the technique that we will use. Okay, so let's see what we have here. So for all x that makes sense inside of 1 over cosine, which could be written as this, pi over 2 plus pi z, or x is not in that set, we have 1 over cosine x is equal to 4 pi times the sum as n goes from 0 to infinity. We have minus 1 to the n times 2n plus 1 over pi squared 2n plus 1 squared minus 4 times x. So just as a gut check, you can maybe set x equal to 0 and notice that you retrieve something like a well-known series over here on the right-hand side, and you'll in fact get the whole series sums up to 1, again because it's a well-known series. Okay, so like I said, we'll use Fourier series to do this, so let's just recall that. So if you want to take a function f of x that's periodic, 2 pi periodic on the interval from minus pi to pi, then in fact we can expand it in terms of sines and cosines like this. So we've got a0 over 2 plus this cosine sum plus this sine sum, where the coefficients of the cosine sum are related to the integral of f of x times cosine nx over that interval. And the coefficients of the sine sum are related to a corresponding integral involving the sine function. So we'll start by finding our coefficients here, but you might say, well, what function are we finding the Fourier series for? You might think that it's 1 over cosine of x, but it's not. And that's actually where the trick is. It's going to be a specially chosen function. And I'll define that function. Well, I'll call it f of x, and it'll be sine of t times x, where t is a variable. Okay, so let's calculate those coefficients. So we have an is equal to 1 over pi, and then we have the integral from minus pi to pi of, let's see, we have sine of tx times cosine of nx dx. Okay, but let's notice that sine of t times x is an odd function. Cosine is an even function, making this product an odd function. Oh, but check it out. We're integrating an odd function over a domain which is symmetric to the origin. That immediately gives us 0. So that's one of these things that you technically learn right after you learn integration, but often it's not taken advantage of as much as it should be. Okay, so anyway, now let's move on to the Bn coefficients, those coefficients in the sine sum of the Fourier series. So again, we've got this factor of 1 over pi, then we'll have the integral from minus pi to pi. Now it'll be sine of t times x times sine of n times x dx. Now before we get started, I've got sine times sine, that's an odd function times an odd function. If we take the product of two odd functions, we get an even function. But an even function over a symmetric domain can be changed. Instead of, in this case, going from minus pi to pi, it will be from 0 to pi if we multiply by 2. So that's a nice simplification. Another simplification that we use is a so-called product to sum identity for, well, in this case, the sine function. And it goes like this. So sine of alpha times sine of beta is equal to 1/2. And then we'll have cosine of alpha minus beta minus cosine of alpha plus beta. So I won't derive that or anything. That's fairly easy to come up with. So let's apply that to this setup. So here our alpha is t times x and our beta is n times x. Okay, so that's going to leave me with 2 over pi, and then we'll have the integral from 0 to pi of, let's see, it'll be cosine of the difference, so that'll be t minus n times x, and then minus cosine of the sum. That'll be t plus n times x. But now the antiderivative of cosine is sine, and then we need to evaluate these at the two endpoints. Okay, so let's go ahead and do that. Oh, but before we do that, I realized that I brought this 2 down, whereas the 2 should have been canceled by that 1/2. Okay, so anyway, now we're ready to take our antiderivatives and plug in our endpoints. So we have 1 over pi, and then we'll have sine of t minus n times pi over t minus n. We get nothing from the lower bound of integration because sine of 0 is 0. And then here we'll have sine of t plus n times pi over t plus n. So something like that. And now we're going to use this kind of nice identity, which has to do with the 2 pi periodicity of the sine function, as well as the cosine function. And it goes something like this. So if we have sine of theta plus n times pi, then that's exactly equal to minus 1 to the n times the sine of theta. So obviously, if n is even, we should get just sine of theta, given the 2 pi periodicity. And then for n being an odd number, you pick up that minus sign. And then this also holds for sine of theta minus n times pi. So that gives you the same object over there. Okay, so what does that mean? Well, that means that we can take this first term and rewrite it as minus 1 to the n sine of, maybe I'll write this as pi times t. And then likewise, this is also minus 1 to the n, and then sine of pi times t again. Okay, so that's pretty cool. Let's maybe bring that up and then we'll keep going. So I did a little bit of rewriting, just like factoring things out. But our bn coefficients, which was all that remained for our Fourier series of sine of t times x, were equal to this object right here. And now I guess the game at this point is to combine these two, things that are rational functions in our variable t. And we'll do that by giving them a common denominator, which will clearly be t squared minus n squared. So to get this first one, we'll multiply by t plus n. That'll give us t squared minus n squared there. And to get this second one, we'll multiply by t minus n. And that'll give us, again, t squared minus n squared there. Okay, so what will that simplify to? Well, we'll have t minus t, so that'll cancel. And then we'll have n minus negative n. So that'll give us a 2n. But I'm actually going to extract a minus sign to flip the order of subtraction here. So we'll actually have minus 2 times n over n squared minus t squared. That'll actually be a little better way to write this. Okay, so now let's kind of bring this stuff down. So that tells us that we have sine of t times x is equal to, well, let's see, it'll be the sum as n goes from 1 up to infinity of minus 2 times minus 1 to the n times n times sine of pi times t all over, let's see, we'll have pi and then times n squared minus t squared. And then that's just the coefficient of our sine nx. So we need to include that there. So we have sine of n times x. And now the trick at this point is to set x equal to something. And it'll be something that's advantageous to simplify that right-hand side. And in this case, we'll set x equal to pi over 2. That will give us the sine of pi over 2 times t. Now, we need to go a little bit more in depth with what's going over here on the right-hand side. So notice this is where the x term is. So what we really need is to determine what sine of n pi over 2 is. And that's going to depend, well, obviously on the value of n. If n is equal to 2, we get sine of pi as 0. If n is equal to 0, we get sine of 0 as 0. If n is equal to 4, we get sine of 2 pi, which is 0. In fact, if n is even, then we get an integer multiple of pi inside of the sign. That will give us 0. So in other words, we'll have 0 if n is even. In other words, if it's equal to 2m. That's how I'll parameterize the even numbers. And then if n is 1, we'll get sine of pi over 2, which is 1. If n is 3, we'll get sine of 3 pi over 2, which is negative 1. And then it'll continue to alternate like that. So we'll be able to write that as minus 1 to the m, and that'll be when n is equal to 2m plus 1. That's how we get it to maybe alternate in the correct way. Okay, so let's bring that down over here. So now we'll have the sum as m goes from 0 to infinity, just based off our parameterization of the odd numbers. And then we'll have minus 2, and then we'll have minus 1 to the n, but now n is 2m plus 1, so that means that minus 1 will always be negative. So that means that'll cancel out the minus sign here. So that means we have 2, and then we'll pick up this minus 1 to the m, that's a new minus 1, and then here we'll have 2m plus 1, that'll be for this n, and then that's going to be all over pi times 2m plus 1 squared minus t squared, and then times, let's see, sine of pi times t from this term right here. So next up, we'll divide both sides by sine of pi times t, and then that'll maybe like help, work towards our next step. Okay, so let's maybe bring that up, and then we're kind of almost there. So this is where we left ourselves off. I did change my index from m back to n over there on the right-hand side, but that's not really that much. And then another thing that I did is I maybe divided the 2 that was on the right-hand side over to the left-hand side, and then multiplied both sides by 4. That just scales everything nicely. Okay, so next up, we're going to take this sine of pi times t term that's in the denominator and rewrite it using the double angle formula, where the angle that we are doubling is this pi over 2 times t. So that'll give us 2 times sine of pi over 2 times t times cosine of pi over 2 times t. And that's where you can see everything maybe falling apart. So now this 2 will cancel this 2. And then next up, this sine pi over 2 times t will cancel this sine pi over 2 times t. So just to like maybe put this all together, that means that what we really have is 1 over cosine of pi over 2 times t. That's how this left-hand side is simplified. I obviously wrote it over there on the right-hand side though. Okay, so lastly, we'll take this entire object and we'll make a substitution. And that substitution will be to set x equal to pi over 2 times t. And see where that takes us. So that'll give us 1 over cosine of x. I'm flipping the equation again. And then we'll have 4 over pi. And then the sum, as n goes from 0 to infinity, we still have this minus 1 to the n, 2n plus 1, and then we have this 2n plus 1 quantity squared, and then we'll have minus 4 over pi squared times x squared. That's what we get just for solving this equation right here for t. And then where do we go from here? Well, I think it's pretty clear that we can multiply the numerator and the denominator here by pi squared. That'll put a 4 pi in the numerator instead of just a 4 in the numerator. And then this pi squared will cancel this pi squared, and it'll multiply through to this 2n plus 1 squared. Oh, but that leaves us exactly what we have over here. Okay, so now that we've derived this identity, I want to see maybe what we could do with it. So using this series that we built together with the standard Taylor series for cosine, we can, well, obviously multiply them and get 1. Or if we move this 4 pi over to the other side of the equation, we have the product of these two infinite series is in fact 1 over 4 pi, and that should hold, well, really for all x where each of them converge absolutely. Okay, so that being said, we could use Cauchy's summation formula to push those together. So I'll let you guys look that up if you need to, but you'll get something like this, which looks a little gnarly. But that being said, I bet you could maybe set x equal to 1, and then you could manipulate this into something that looks at least a little bit surprising. And that's a good place to stop. Thanks for watching and sticking around until the end of the video. And since you're here, don't forget to gently press that like button, subscribe, ring the bell, and select all notifications to never miss a video. If you want to get your name in the credits like you see here, access the live seminar series, review videos before release, and more, go to patreon.com/michaelpennmath and become a Patreon member today. If you want full ad-free course content, subscribe to my second channel, Math Major. I've got courses on linear algebra, complex analysis, and proofwriting, among several others. And that's everything. Bye.